The most important thing to remember about computing probabilities is it's impossible to compute most probabilities. So let's compute some probabilities. The very few cases where we can involve equally likely outcomes. A sample space consists of equally likely outcomes if, for any outcomes in our sample space, the probabilities are, and here's the complicated part, equal. Equivalently, all outcomes have the same probability p. As a general rule, a given sample space will not consist of equally likely outcomes. If you think it does, see the first note. And if necessary, we might assume, and importantly state that we're assuming, that the sample space consists of equally likely outcomes. And that's because we can assume anything we want as long as it's explicit. So let's consider a finite sample space of equally likely outcomes, where the probability of any outcome is p. Since the events consisting of the individual outcomes are mutually exclusive, we have the probability of S is the probability of the union of all of these events. Because we have a probability measure, the left-hand side is 1, and the right-hand side is the finite sum of the individual probabilities. And since there's n outcomes, that's going to be np, and so the probability is 1/nth. And this gives us our theorem. If S is a sample space consisting of n equally likely outcomes, and x is an outcome, then the probability of that outcome is 1/nth. So, suppose the 365 days of a year are equally likely dates for someone's birth date. What's the probability a person was born on July 18th? By explicit assumption, each date is equally likely, and there are 365 days, so born on July 18th is a single outcome in that sample space, so the probability is 1/365. Now let's move on to events. Suppose S is a sample space of n equally likely outcomes. Let E be an event with k outcomes. What's the probability of E? So without loss of generality, we'll assume that E consists of the first k outcomes. So again, we can write this event E as the union of the events consisting of a single outcome, which are mutually exclusive. And so we could rewrite this as the sum of the probabilities of the individual events. But we know the probabilities of the individual events, it's 1/nth, and so our probability is k-nth. And this gives us the theorem. Suppose S is a finite set of equally likely outcomes, and E an event. The probability of E is the number of outcomes in E divided by the number of outcomes in S. So suppose the 365 days of a year are equally likely dates for someone's birth date. What's the probability a person was born on the 31st? So a person could have been born on January 31st, February 31st, March 31st. Oh, wait, no, let's see. 30 days, half September, all the rest I can't remember. Give you a moment here. Let me check the calendar. Oh yeah, so only 7 months have a 31st, so a person could have been born on any one of those 7 dates, and so our probability is 7/365.